Hello, this is Mr. Gilmore with the 9.5 Corollaries of the Tangent Existence Theorem and its Converse. Now, we saw in the last lesson, 9.4, that we do actually have this creation of this existence of this tangent line, which actually then enables us to actually create or construct any line tangent to any given circle. We know that that line is defined and that that line exists thanks to our theorem. We also saw that with its converse that whenever you do form a tangent line to a circle, that it's then provable that to the point of intersection of that point of tangency it is perpendicular to the radius drawn to that point of tangency. Well, what we're going to do today in the 9.5 lesson is follow up with several corollaries or theorems that we can actually prove using the tangent existence theorem and its converse. Let's dive in then to our first theorem. Let's take a look at what we call the twin tangent theorem, or to us, the TTT. So the tangents from a point to a circle are equal in length. Essentially, imagine given any circle and a point that are coplanar. This point then chosen is going to be on the exterior of our circle, and what we're going to prove then is that the tangents that we can construct from that given point, such that we actually intersect at the circle at 2 points, two distinct points of tangency, that the segments that are going to be formed are actually equal in length. Let's take a look at our diagram down below. We've got our circle A given to us such that there are 2 points of tangency, point B and point C. And these points of tangency are actually both drawn from the given point D that is on the exterior of our circle. We can actually prove that the segment produced DB and the segment produced DC are actually equal in length. Let's take a look at the proof of the twin tangent theorem. So with our given, we're actually going to make a few constructions to start off with to begin the proof of the the twin tangent theorem. So what we're going to do first is with our given points A, B, C, and D, we're going to connect point A to B and point A to C. Now we'll find there in just a moment that AB and AC are going to be equal in length because they're both radii of the circle. But we're also going to do one more construction. We're going to connect point A to D. And because of that, what we're going to find then is that we formed actually two triangles. We have triangle ABD and triangle ACD. And we're actually going to prove that those two triangles are in fact congruent. And if we show that those two triangles are congruent, then we know that their corresponding sides, DB and DC, will be equal in length. Let's follow through with what this proof unfolds. So after our construction, we can immediately claim that AB and AC are equal in length, which means we already have one pair of equal sides equal between these two triangles. We also have a common side, AD. Okay, AD is common between, so it means we already have two sides of one equal two sides of the other. Now, one last piece of information that we're actually going to use is thanks to our converse of the tangent existence theorem. We know that whenever a tangent is constructed to a circle, that point of tangency where the radius meets that tangent line is actually perpendicular, which means we've got ourselves right angles. ABD and ACD are actually right angles by that converse of the tangent existence theorem. And because of that, we are now dealing with right triangles. And it just so happens that AB and AC, those radii, are actually the equal pair of legs of our right triangles. And AD is a shared side or a common side, which is the pair of equal hypotenuses. And because of that, we have ourselves two triangles that are congruent by our special case hypotenuse leg, or HL. Which then means, by our good pal CPTCE, we have DB and DC are equal in length. So now whenever we encounter a point that is on the exterior of a circle, such that we draw the two tangent segments from that point to our given circle, we know that those two produced segments are actually equal in length, which we will see the use of our twin tangent theorem, the TTT, come up here in just a moment to help us prove some other results. So the next result, this theorem doesn't really have a name, but what it really is a corollary of a corollary. This is actually a quick follow-up from our twin tangent theorem that we just saw on the last slide. What we can actually prove then is that if you're given two circles, that their common external tangents are actually going to be equal in measure. So one name we could probably come up with this theorem is call it the common external tangent segment theorem, which is a mouthful. But what we're going to show here or demonstrate here in just a moment is that with the two circles given to us below, that there are two segments, AC and BD, and we're going to prove that if what we're given then is points A, B, C, and D, all 4 points are points of tangency, which means the two segments there are tangent to each of the given circles, we're going to prove that those two actually are equal in length. Now, I'm going to let you guys put the details together of this proof on your own, but I'm going to give you a nudge in the right direction. Essentially, what we're going to do with each of the segments is we're going to extend them out through one of their points of tangency, and we'll find then that we will find then a point of intersection that will be external to both circles, and then what we can do is actually apply the twin tangent theorem. So I'm going to extend our first segment CA through point A. Okay, just a given length. I know there's a line that exists between those 2 points, so I'll just extend along that line. I'm also going to extend through DB. I'm going to extend through point B such that those two extensions actually intersect, and I'm going to call that point Z. All right, you can call really whatever you want to. I'm going to call mine Z. Now, you're going to then continue to work your way toward proving that the segment AC and BD are equal. But notice what you know about this new point Z. It's external to both. It's external point to both circles, which means what do you immediately know about this length AZ and BZ? That those lengths are equal in length. And what do you know about the entire length CZ and the entire length DZ? You know those are also equal in length. Use that then to arrive at your conclusion that AC and BD are actually equal in measure as well. And I'm going to leave the details of this proof up for you guys to do on your own. Let's continue on into our journey with some other corollaries. So before we get into our last theorem, I want to introduce another definition. We have the definition of inscribed polygons, where we found that the vertices of our polygon were all on the circle. Well, now we can actually have what's called circumscribed polygons. A circumscribed polygon is a polygon such that all of its sides are tangent to a given circle, which means we'll find that with all of the sides, whether it's a triangle or quadrilateral or pentagon or 100-sided gon, we'll find that there will be an equal number of points of tangency as there are to the number of sides. And so we find below as an example of a circumscribed polygon. It's actually a circumscribed quadrilateral. So we have the quadrilateral BCDE, which is circumscribed about circle A. So notice that BE, BC, CD, and ED, all four sides of our quadrilateral, will actually find points of tangency here based on what we have defined as what we call a circumscribed polygon. Well, what this is leading us into is actually a special theorem known as the circumscribed quadrilateral theorem. Let's take a look at what that theorem actually says. So the circumscribed quadrilateral theorem says this: if a quadrilateral is circumscribed about a circle, then the sums of its opposite sides are equal. In other words, let's actually take a look at our example below and use that as help to actually show the conclusion or the result of our theorem here. So we're given this circumscribed quadrilateral, and what we're going to prove is that the sum of the opposite sides are actually equal to each other. In other words, take the segment BC, which is this side here, add it to its opposite side, ED, and what we'll find is that the sum of those two sides are actually going to be equal to the sum of the other opposite pairs of sides, BE and CD. So that's going to actually what we're going to arrive to in our last slide here. We're actually going to prove our circumscribed quadrilateral theorem, and I'm going to help you with this one because you can get lost in the detail very quickly. You have to make sure you set up the appropriate addition segments as we dive into the proof of the circumscribed quadrilateral theorem. So let's take a look at this proof together now. So we begin again with our given, which is that BCDE is circumscribed about circle A, which does then mean by definition that there are 4 points of tangency. And you'll see that I will actually label these points of tangency within our proof. So let's begin. BCDE is circumscribed about circle A. Label the points of tangency for BC, CD, DE, and BE as W, X, Y, and Z, which respectively, which means we're going to start here with BC. We'll call this point here W. We'll move on to the next segment, CD. We will call that point X. And then we move on to our next segment, DE. We'll call that point Y. And then our last point of tangency here on BE we'll call point Z. Now, this is where the fun begins, because now notice that with B, C, D, and E, all exterior of our circle, we have then the twin tangent theorem to come and help save us actually arriving to our conclusion that BC plus DE is actually equal to BE plus CD, meaning that the sums of the opposite sides are actually equal to each other. So how do we derive that using our twin tangent theorem? Well, first then is I can actually mark some of these segments as being equal. I know that BW and BZ will be equal. I know that CW and CX will be equal. I know that DX and DY are equal. And I know that EY and EZ are equal as well. So how does this help us? Well, I'm going to then strategically add equals to equals such that then the sum of those parts will end up equaling the whole. Let's begin then on the left side of our equal sign. I'm going to take first this segment BW and the segment CW and add them together. I can add equals to equals. But what that also means is I have to add their equal counterparts to the other side, which means you'll also see that I have BZ and CX added on the right-hand side. And then I'm going to add again to the left-hand side. So on the left-hand side, I added BW and CW. I'm also going to add DY and EY together on the left-hand side. But that also then means if I'm adding EY and DY on the left hand, I have to add equals to equals on the right hand, which means I will also add EZ and DX on the right-hand side of my equation. And what we'll then find is that with BW and CW, they add up to the whole by segment addition postulate. They add up to then BC. And EY and DY, they also add to the whole, which is then DE, which means we've already got then the sum of our opposite sides. Well, then watch the magic that unfolds as we look at the right-hand side, because if we're adding on the right-hand side BZ and EZ, they equal the entire segment BE by segment addition postulate, and CX and DX also add up to their whole, which is CD, and thus we have it BC plus DE equals BE plus CD, or in other words, the bigger picture, that the sum of the opposite sides are actually equal to each other in a circumscribed quadrilateral. So that actually then, QED, concludes our proof of the circumscribed quadrilateral theorem, which you will be using on the worksheet tonight. So be sure to take a good look at using these theorems. So hop over to the 9.5 worksheet and begin working through using these corollaries of the tangent existence theorem and its converse. Really, thanks to its converse helping us prove the twin tangent theorem. The twin tangent theorem actually helps us prove all these other corollaries that immediately follow, knowing that the twin tangents are actually equal to each other, right? As choosing any point on the exterior of our circle, forming that pair of tangents from that given point, we have proven those segments to be equal. If you do have any questions on that 9.5 homework assignment, please do not hesitate to email me. I will get back to you as soon as I can. With that, be good and do good.